Hi guys. Today what we're going to be talking about is an experiment in order to measure the Earth's magnetic field. But before we do that, we want to get the orientation of the field right. So what we're really seeking out when we're using a compass is the North Geographic Pole. In general, when we are using a compass to determine north, this north is geometric north, and what we do is we can compare the Earth's near dipole field to a short magnet, as you can see below, with its south magnetic pole, which points towards the Earth's geometric north. So you can kind of get a general sense of this, and that was Semantic, with I think Physics Today, but I have it quoted there, and but basically you can see it here with this bar magnet experiment here. It's a demo. It's a simple thing to measure the field lines around the bar magnet. We do know they're closed loops, but the bottom line is that the compass is pointing towards the north as the field lines are plotted, and we can kind of see that there. Now if we move a little bit this way here, this is the real, this is really how the Earth's magnetic field is oriented. It's dipping below the horizontal. What the compass is giving us is it's giving us the Earth's horizontal field. So if we use a dip compass, we can get that angle, and we can compare that angle with the NOAA magnetic data website, and that would give us at our location and the time of day what the dip angle should be. Now we can use that dip angle there to actually measure the magnitude of the Earth's magnetic field, but we would need a couple of things. And basically we would need what's called a tangent galvanometer, pretty much a compass, a ruler, and a power supply, and we'd be pretty good. But we'd have to make sure that we're away from electrical sockets and stuff, because that would interfere with the data. So what we would basically do is we would run a current through that tangent galvanometer, and it would produce a field that would deflect the Earth's horizontal field. So we would kind of get what's called Biot-Savart's law to model the magnetic field produced by the tangent galvanometer, and that's just kind of geometry there. So, but this here is pretty much what we're really looking at here, that as there's a current run through that tangent galvanometer, what we're going to do is we're going to get a field from the coil building upward, and it's going to deflect the Earth's horizontal field, and we're going to get a net field there. So that d theta there represents that change in the angle over time as we increase the current over time. Now the Biot-Savart rule is given by B coil there. It's really for a solenoid because the tangent galvanometer acts as so. So it's the number of turns, and that's kind of given on the tangent galvanometer, sorry. Mu zero, the constant of free space, and I, the current, over 2 times the radius. And but if we plug that in to the relationship here that we get, B coil over B Earth horizontal is really going to be equal to tan theta, right? We can come up with a formula for the Earth's horizontal component. And basically, so there's kind of the mathematics behind it, and you can see the formula here. And it's broken down because we're going to be really collecting current and angle data. As we increase the current, the angle deflects, the angle of deflection increases. And if we then graph tan theta on our x-axis and the current on our y-axis, what we would get is we get a straight line, and if we take the slope of that line, we're going to get that change in I over change in tan theta, that rate, and then we can plug it into this formula here where mu zero is 4 pi times 10 to the negative 7, and we've got 2 times the radius, so we can measure the diameter of the tangent galvanometer divided by 2 and plug that in, and the number of turns is actually given. We can see here that's given on the tangent galvanometer. So if we go back up here, you could see it's a little hard to see, but basically if you zoom into this picture here a little bit, you would see that we have across here 15 turns. We have like 5 turns and then like 10 turns. So it depends where you are and what end's going to be there. Okay. And then from there, once we get that slope, plug it in, and find the horizontal Earth's field, we can then take that dip angle. And what we can do is we can, we would have the dip angle and now the horizontal component. And then we can find the resultant vector, which would be the Earth's field at that dip angle using that data. And also it's a good idea to go to the NOAA website and get a more accurate value of that dip angle, because there are electrical components in the room, so that will affect that too. So it's a little tricky. The data on measuring the Earth's horizontal component is pretty good. Usually it's around 2 times 10 to the negative 5 Teslas, so it's not too bad. And then so getting the Earth's field is pretty close as well. Well, that's it, guys. So that's the experiment, and generally the experiment was to first show the orientation of the compass, that it points towards the South Pole. Well, what does that mean? And it's really pointing geometric north. Sorry, I kind of said that a little off there. Geographic north, sorry. And then we gave a way of actually calculating the magnitude of the field, and we can use the dip compass to get the actual direction, which is really not horizontal, but it actually dips below and stuff. So thanks, guys. That's it.